Welcome back, everyone, to the super ghetto GTX 960 repair that I did the other week. When I originally put this thing back together, I did a really ghetto video, which was supposed to be a little bit tongue-in-cheek because I genuinely didn't think it was going to work. This card had literally caught fire. There was smoke and there were flames. And that was after it had already been short-circuited. I genuinely didn't think it was going to work, which was why I was dicking about so much in that video. But it turned out that it did work. So a lot of people were saying in the comments sort of, oh, you know, you just got to do this, that, and the other, and that'll be fine. And at the time, I was like, yeah, it would. So you know what? Let's fix it properly, because why not? And we can just demonstrate that can be done. So I went away and I've ordered some parts. So firstly, we've ordered a new set of MOSFETs to rebuild the VRMs. And then the second thing that we needed was we needed a new cooler and we needed new input inductors. Now that was the trickier bit, because the input inductors, I have absolutely no clue what rating that they should be. And I didn't want to just leave them off the board, because then there would be no input protection should the card go short circuit again. And likewise, finding a replacement cooler for minimal cost was also difficult. I thought that when I looked on eBay, I would find just second-hand graphics card coolers left, right, and center. But at least on eBay UK, that was actually easier said than done. In the end, I actually bought another GTX 960. This is actually an identical model. It's also a Dell OEM 960. As you can see, this is a reference card. And I bought this. I paid £20 for this fella. And it does work. However, apparently the computer crashes after approximately 20 minutes of use or so. I haven't actually tested this thing, but if it's crashing after an amount of use, it obviously has some kind of thermal issue in it. Part of me was tempted to investigate what fault this one actually had. However, I don't really care. I'm just going to use it as a donor card. I have a suspicion that, like, apart from the faulty bits on this one, like the cooler and the VRMs and things, this card is a known good, because we did actually burn test this one and it got through a burn test. So we're going to fix this one, and then after I've robbed all the parts from this, I'm actually chucking this one in the bin, because I'm not going to get into an endless cycle of now we've got to fix this one. We're not doing that. I'm going to fix this one, and that's the end of this. I am not going into a cycle. Anyway, let's get started. The first thing I'm going to do is I'm going to take both the cards to bits again, and we're going to identify what parts we're swapping out and what parts we're replacing. So I'm going to start just by taking the coolers off of both cards again. So let's go. There we go. Right, we got there in the end, after missing half a dozen screws. Cool. So this one, we should find is an identical card, and yeah, it is. So we've got the input inductors in the top right here that I want to steal. And condition of this one, it looks pretty good. I'm just going to undo those push pins and take off the VRM cooler as well. That's the other thing that we want to steal from this card. We want this VRM heatsink, so we can ditch our ghetto M.2 one, which could have been adapted. There was one person in the comments saying sort of, oh, you could drill some holes in that so you could bolt it down properly. Absolutely, I could do that. However, now I have a donor card, so I don't need to, which is nice. There we go. So we've got a known good heatsink and known good VRM cooler. Just going to see, can I remove that from there a sec? Yeah, so this one's seen some usage because it had been cleaned up beautifully. This one, like, look at that, it looks pristine. However, you can tell that it's actually seen some heavy usage. This wasn't. Yeah, so there's always going to be some stuff hiding in there somewhere. But you know, we can clean that up. That'll be fine. I would wager that this reference cooler is probably just as good as the Zotac one, to be honest, because that Zotac cooler is nothing to write home about. If it was a twin fan blower or something like that, I might care about it, but yeah. Right, let's just take the worst of that off. So on this one, there doesn't appear to be any visible damage to any parts of it. So we could take all the MOSFETs off of this one and use them on this card. Actually, let's see if it's the same ones first as well. It almost certainly will be. But again, we'll do a quick comparison just for posterity. Okay, so we've got PK632BA. Oh, these ones are different. That's interesting. Oh, now you got me curious. I think the ones on my donor card are worse because they don't have a brand name on them. I'm just going to look them up just out of curiosity. Okay, it's an on semiconductor. So yeah, it is a branded one. Well, this is interesting. What I'm going to do now then is, firstly, I'm going to go and get the new MOSFETs I've bought, and we're going to bring up all of the data sheets so we can actually check if they're both the same spec to see if both of these cards were born equally. They've got different memory on as well. This one's got Samsung on it, whereas this one's got SK Hynix. But having different memory chips on a per card basis isn't entirely surprising, although considering these are identical models, that's kind of interesting to me. So yeah, I don't know how much in proof there is out of any of this. I'm just curious as to what the differences are, just as an intellectual venture, if nothing else. Just learning more about graphics cards, basically. Right, be right back. Interesting. So comparing the ratings for the two MOSFETs that we've got across the two boards, they're fairly similar in spec. The numbers differ ever so slightly, but also they're being compared in different ways. For example, this datasheet is comparing operating temperatures from 25C to 100C versus the on semiconductor, which is running 25C to 80C. So we're getting two different points of comparison here. And that means that the numbers are harder to read. But I mean, looking at a brief glance at the numbers, they are comparable. So what we can see here is probably the same reason as to why they both have different memory chips on them. Manufacturing will basically use whatever parts are cost effective at the time of this particular production run. But the cards have both been made to approximately the same specifications. So yeah. So in terms of the MOSFETs that I have purchased, and I've just realised that the MOSFETs I bought are for a completely different project that was abandoned. Oh, that sucks. I was ready to do this tonight. Okay. Well, I'll see you guys after the cut when those MOSFETs have actually been delivered. And in case you're wondering, I don't want to use the MOSFETs from my donor board because I don't know what's wrong with this graphics card. And because this is a similar graphics card that's probably come out of a similar computer, it's also got the darkened PCB on it. These things have probably been cooked to hell as well. So I don't really want to use any actual power components from this. Those input inductors, those guys will be fine. But the MOSFETs, I have no idea what condition those are actually in. So, damn it. Okay, I guess this is all going back on the shelf. So, yeah, see you guys after the cut. Guess I'll work on a different project tonight. At this point, it seems prudent to me to give you a very brief crash course on how buck regulators work to help you better understand this video if you're trying to learn along with me here. So firstly, in a multi-phase VRM setup like what we're dealing with here, the reason why we need all of this fancy stuff to power the chip is that we've got a high voltage input at say 12 volts and we need like 1 volt at the output. But also that 1 volt needs to be incredibly stable. And because it's a high powered device running up to the hundreds of amps at 1 volt, we also need very high amounts of current handling there, which is why we need this very fancy multi-phase VRM setup in the first place. So how a buck regulator works in short. You have a controller chip, you have a couple of MOSFETs, and you have a coil. the control chip switches on the high side MOSFET, and 12 volts will flow through that MOSFET and into the coil. The coil will resist the change in current flow, so it will try and block that incoming current, and instead it will build up an electromagnetic field, so there's only a small amount coming out the other side. And then, just as it can't take it anymore and the voltage and the current is built up too much, the control chip will switch off the high side MOSFET and switch on the low side MOSFET, which will then drag all of that residual voltage back down to ground again. Now, once again, the coil will resist this sudden change in current, and the electromagnetic field inside it will collapse and come out in the form of more voltage. So the result of this is you have spikes of 12 and 0 coming in as the MOSFETs turn on in an alternating fashion. However, at the coil is resisting these steep changes and smoothing that out into an average curve. So if you're switching in 12 volts with lots of zeros between, so just small pulses of 12 with lots of off sections, the average of that is going to be very low, say about 1 volt. So coming out the other side of the coil, you'll have just a steady 1 volts instead. So on one side, we'll have these big spikes of 12, and on the other side, we'll just have 1. And then there'll be a load of capacitors between the coil and the actual GPU that then also helps smooth all of that out and just smooth out any bumps and ripples. And also, for example, if the GPU suddenly takes a gulp of current because it bangs onto load, there'll be a load of capacitance there to provide that extra power while the buck regulator picks up the slack. So that is the very quick short answer on how buck regulators work. I do have a video on how to do this. If you search my channel for buck regulators, I've got another explanation of this with visual stuff, but that's the short of it. So let's get back to the card where I now have my MOSFETs. So being a OEM reference card, none of these MOSFETs are particularly exotic. However, the low side MOSFETs are slightly stronger than the high sides. And so what I did, I ordered a pack of the stronger ones on the board, basically. I looked up the data sheets for all of them, and I think there should be 10 here. Yeah, I got 10 of the stronger ones. So I don't know if that's not going to be enough to do everything. However, we should be able to replace all the ones that we need to. So the first objective, obviously, is to get this card to a true working condition. I've got a donor card here, which has some other unknown fault that I'm not going to investigate because I don't care about this card. I don't want to fix this one. I just want it for parts. We're going to take the input inductors. I'll tell you more about those in a moment. So we're going to take the input inductors off of this one and put them onto here so we have a proper power induction. And then we need to, top priority is to replace these missing MOSFETs here that we took off because the high side was shorted to ground. So we want to take all of those out. And then while we're at it, so that'll be 3. Then while we're at it, I'm probably going to replace these ones as well. So that'll be 6. And now I realise that really what I should have done... oh no, then we can replace those as well. So we can replace all of the MOSFETs on this one. That'll be 9. Or another option that I have also considered is to populate this missing phase here. So we can turn this 2+1 into a 3+1 perhaps. But before I do that, I'll have to have a closer study on what the VRM setup here is to see if I can actually do that and bump up the abilities of this card. So we need to have a look at the power management IC, which is probably this guy here, and see exactly what it's capable of and see what configurations it might be in. But in all probability, we should find that these are all commoned up. So let's just check that. Yeah. This is ground anyway, I believe. Oh, apparently not. Oh, okay, this phase is this bit here is not connected up to there. That might be That might be to do with this missing coil, though. Not 100% certain. Oh, actually, is it paired to this one? No. Yeah, that's fine. I didn't expect it to be. This phase here is powering the memory, so this one is probably standalone, which is why it's all in a slightly different orientation to this one. Interesting. Okay, I'm going to have a really close look at a couple of these chips and find out what controller we've got on here, just so we can learn a bit more as we do it. Then what we'll do is we'll start building this card back up into a working state. So I'm going to pause for a sec just while I have a close-up on a couple of things. Okay, starting with this guy, which is an INA 3221. Let's look that one up. Well, that's interesting. It's not a PWM power controller. It's just measurement. So this is literally just power monitoring. So as you can see in here, it is 3 channels, but it doesn't run power for anything. It just senses power. So you can see we've got we have a shunt resistor measurement system for each one, and it just switches between them. So that's kind of interesting. So this is not power management, it's power monitoring. So this will probably talk to the power management IC or to the GPU or general management to find out how much power the card is using, but it doesn't actually handle power by the looks of things. Cool, all right, so what does? Aha, now this looks a lot more promising. On the other side of the board, we've got an on semiconductor here. That's an NCP81174. Let's look that one up. Now that's more like it. So this is a 4-3 or 2-phase buck controller. So this is what we're looking for. So firstly, confirmed it can do up to 4 phases. So now what I want to know is, can I determine how this thing has been configured on this board so I know whether it can be adjusted or tweaked to run additional phases? So we've got to bear in mind that there's not going to be a separate controller for the memory. It's almost certainly being controlled on the same power controller. So we've got at least 3 phases in use already, but we know that this thing can actually do up to 4 phases now. So can we get it into 4-phase mode if it's not already? So let's have a quick look through this thing. So we've got our pinouts. So here is a typical setup. I'll just zoom out slightly to fit that on the page. So you can see we've got a controller, and then you have your 1, 2, 3, 4 phases here. What are they showing as those actual phases? So they're using something else, typical 4-phase application with PWM VID interface. Now, I think I might know what those are. These chips here, I think, be quiet. I think those are these little dudes here that are sitting next to the MOSFETs. So I think what we've got is our power controller is... So our power controller is on the back of the board, and then when I turn it over, that is then wired into these 3 little chips here, which then go through to the MOSFETs. So we've got power controller and those 3 little chips. And then those chips connect to the MOSFETs. Those are Q1, 2, 3, 4, and so on. And so we've got, in this instance, the typical application is showing 2 MOSFETs per phase. However, you can easily, this is just a suggested application. Technically, there's nothing stopping them from adding in additional MOSFETs here to bump up the efficiency or current handling of the circuit. So they've labeled this as with a CPU output, but again, this is a recommended application. In this instance, they're using it to run a GPU, which is, as far as this power controller is concerned, more or less the same thing. It's a high power, high precision chip that needs a multi-phase power supply. Okay, so this does pose a question, because we've got 3 of those controllers and one of them on the board is missing. So here's an interesting thing. Could I add in a 4th, because I've got a donor board with more of them on? So could we add in the missing 4th one? Because we've only got 3 of these chips. Number 4 here is missing. So could we add in the 4th and turn this into from a 2+1 into a 3+1 power supply? and that theoretically would provide more power. Now, this isn't going to make the card better in any meaningful way, but the point is to demonstrate how these power systems work and how you can modify them. Okay, so reading through this section here on the detailed description, it says here, so this is the general information, blah, blah, blah. It's very compact, it's very good. Now, here's the interesting bit. It's got 3 styles of operation. It has one-phase force PWM mode to obtain high efficiency. So it's got a power-saving mode, and then it also has, well, an intermediate and a low. TLDR is, you read through this and it tells you to skip down to the tables. So you follow this table. It's not important which one we're on at the moment. This is down to what kind of voltage you're driving the chip with. But the main point is that it's got a high, an intermediate, and a low. And if we have a look at this, in low, it's got one-phase auto. So it's going to be in single-phase mode, and it's going to use diode emulation, which most likely means that it's going to use a high-side MOSFET and a freewheeling diode effect. Then in the intermediate mode, it will just be single phase with high and low MOSFETs. And then in high power mode, it will run all phase. It says full phase there. And then that signal for what power state it's going to be in comes from will probably come from the GPU, which will then send its instructions to this chip to say how much power it requires, or from elsewhere in the board. So the main thing is that there doesn't seem to be any differentiation as to whether it's in 1, 2, 3, or 4 phase mode. So my guess is that all the phases are enabled. It's just a question of how many of them are populated on the board. So it seems prudent to me at this point as a layman that we can just populate the missing phase. Yeah, this is all timing stuff. If we just populate the missing phase, then we'll get a 4-phase system. So let's roll back up to the top and go back to that circuit diagram. So basically, we've got 3 phases are hooked up, and we've just got to populate the last one. But I think we'll come back to this later on in the video. Firstly, let's get this card repaired, and then we'll see how much we can push the envelope on it. So what we're going to do first is let's switch back to the board. And on the board, the first thing we need to do is we need to repopulate the input inductors here. Now, previously on this board, all these input inductors had been blown up by the previous power event that this card had suffered. In the previous video, I shunted these out. However, as you can see, I've cleaned all this up. I cleaned that up in a more recent video. But we still need to actually fix this. So what these do, if I switch over to the donor card, which has them currently populated, so there are the input inductors. Now these guys, to the untrained eye, they look a lot like capacitors, because these two are capacitors. However, these are grey and these are brown. That's the first giveaway. They're also labelled as L on the board, not C. L is the designator for an inductor, also known as a coil. So what these are, this is inrush protection. So basically you've got power coming in through here. It goes through all of these, through this current sense resistor, and then into the rest of the power system on the board. And these are essentially, they're just fuses. What an inductor does is that it resists a change in current. So when you plug this in and the board powers up, if there's a sudden surge of power going through, these things will resist that. It will slow it down and let it funnel through in a controlled manner. It's like having an elastic band on things. It's like an elasticated tow rope. Instead of just viciously tugging on the rope that is the power source, it puts some elastic in there so it can go and pull and follow. And that stops a sudden surge of power that might overload other components. And then the reason why we've got lots of small ones there is it means that they double up as fuses. If there is a massive overcurrent event, it will just blow these up. And essentially, these things getting exploded is probably what saved this card from its previous short circuit in the first place. So they very much did their job. When we did the bodge repair on this card, I just bridged this out. However, that's not ideal long term, because if another MOSFET goes down, it means there's going to be no protection against inrush current. So if the card goes short circuit because of another blown MOSFET, that basically means the card will pull the amount of power that the power supply can deliver. And if you've got it hooked up to a kilowatt power supply, that means you're going to dump a kilowatt into the rest of your MOSFETs, and there will be smoke. So first thing we're going to do is I'm going to move all of these inductors from my donor card over to this card, so we've got a nice input set up again. So I'm going to hot air these off of the board, and we'll put those on there, and then we'll have a look at what we're going to do with the MOSFETs. So let's start by getting parts off this board to put onto the other board. Right, so I've got my hot air on, maximum airflow, 400 degrees, and I'm just going to apply a bit of heat to the surrounding area. I haven't taken any steps to remove plastic surrounding parts here, but this is the donor board. Don't really care about this one in the slightest. So let's just put a little bit of heat down there, and then we're going to just take all of these off. Once the first one starts budging, the rest will follow really easily. I've got nowhere to put them. I'll just put them on the mat. And no, I don't need that tiny little capacitor. Right, that's that. Now let's bring in the repair card, and I'll just quickly remove this connector just so that doesn't get damaged. I'll just put a prying tool under that and just pop that off. Right, and I'm going to use a bit of soldering iron as well for this now. Right, we've got some flux on the board, and we're just going to put a little bit of solder on all of those pads, just so they're nicely tinned up. Now, if we were going to soldering iron hero this, as I said in my recent video about SMD soldering, I would only tin up one side of the pads. However, we're not going to soldering iron hero this. We're going to hot air it, because we've got quite a few components to put on. If there was just one or two, I'd soldering iron hero, but when you've got many, the hot air makes it much faster. Okay, here comes the hot air. And while I'm just blowing some hot air at the area, I'm just going to add in our inductors. I'm going to have to turn my airflow down because I'm probably going to blow all of these away in a minute. Oh, they've all gone crooked. It's alright, that'll fix in a minute. Right, now I've turned my airflow right down. Oh, I think we need a bit more than that. That'll do. Just get these guys to separate again. As you can see, they're all just flowing into place under the hot air. And that is as good as straight for me. Go on, get in there. That'll do. I'm going to quit while I'm ahead. Turn the airflow back up so it cools down quickly. That was remarkably slick. And now what I'll do, I'll just get the soldering iron and I'll just touch up the sides just to remove the excess solder blobs. This bit is optional, but I'll do it because I can. So we're just taking off any excess solder that's come out the sides, and I'm just scraping it off on my soldering iron cleaning pad. There we go. Right, that's that done. I'll give you the close-up of that so you can see what we've got now. So as you can see, it's a little bit sketchy just because those pads have taken a lot of punishment. They've been blown up and they've been resoldered with very little care several times. However, those inductors are now in place. We now have input protection. So that's that. So I'll stick some alcohol on that just to clear up the flux schmutz. There we go, that'll do. Right, input is done. Put that in place. That's the fan connector, by the way. Okay, right, I'm going to take a break and now we'll move on to these MOSFETs and we'll decide exactly what we're going to do with those, because I'm beginning to wish that I'd bought more than 10 MOSFETs. I thought 10 would be plenty. However, well, we'll see. Okay, right, so I've done a little bit of pondering on the path of procedure. When I ordered the parts, I wasn't planning on building up the missing phase on this card. So I don't have enough replacement MOSFETs to change out every MOSFET on the board. So I'm going to be a little bit selective. So as I previously mentioned, there are two different MOSFETs here. These high side MOSFETs are different from the low side MOSFETs. The high side MOSFETs are essentially just slightly weaker ones. They're just ever so slightly weaker, slightly cheaper. I don't think they're functionally identical. I don't know why they bothered putting a slightly weaker one on them. Maybe just when you're making in volume, saving that 1 or 2 cents on the slightly weaker MOSFET versus the slightly higher rated ones. Perhaps that just makes a difference when you're making in volume. I'm not sure. I don't think I'm missing anything, but we'll find out, because what we've got is the high sides were, these are NICOS MOSFETs. They're PK161BA on the high side, and the low side MOSFETs are PK632BA. And so what my plan is I'm going to put, so the ones I've bought are more of these. So we're going to put 2 new ones there. And then I'm going to take these two, I'm going to take this one off as well. And we're going to put 2 new ones there and there as well. So we'll have 6 matching ones. And then just for good measure, I'll also replace this one with a 632 as well. Was it 632? Yeah, with a 632. So then all 3 existing phases will all have matching FETs. There'll be a mixture of some new and some old ones there, which is obviously a little bit sketch. However, that will mean that I have enough MOSFETs later on to then attempt populating the missing phase here. So we're going to start off with that. Then we'll have enough of it built up to build the card back up and see if it still works. And then once we've got a working card, we're then going to go in all the way. We're going to go whole hog, and we're going to try and populate the missing phase and turn this 2+1 into a 3+1. So, and again, I say +1. Technically, it's just 3 straight phases at the moment. However, I'm calling this the +1 because this is going to memory whilst the other ones are going to the GPU. So let's start off by removing that MOSFET, and then I think then we'll just go in with some new MOSFETs. Let's do it. Right, warming up the hot air. Let's go. And for the record, I'm sorry that it's a little bit dimmer than it was. The battery in my work light has gone flat because I forgot to charge it because I'm a dunce. So, right, these guys are going to put up a bit more of a fight to come off. So I'm going to start warming the board while I position it on my heat mat that is actually the cover of a graphics card, while I put my finger in the thermal paste on the GPU. Alright, there we go. We are roughly aligned. That'll do. And I'll stick some flux on there as well, just to help spread the heat about. Lewis Rossman does it, so it must be right. I remember the previous ones put up quite a fight. So Sometimes it takes quite a lot of nerve to do this because you have to sit here. It takes a long time when you're using a cheap hot air gun like mine, and you sit here thinking, surely I'm cooking it. Surely this thing is getting baked. But it works the last time. Oh, there it goes. And off you come. Right, I'll put that to one side because although it's a MOSFET that we're not going to reuse, it does still work. Oh yeah, and we want this one as well. Let's do this one with no flux and see if this is still a problem. Might not be a fair test because there's a lot of residual heat now, but we'll see. Oh. What the heck? Oh, hold on, different tweezers, different tweezers. Oh. Go to the finer tweezers that can grab a little bit better. Oh, we've lost it. Oh god, that was universally awful. I hope I haven't knocked that capacitor off. That'll be a pain in the ass. Yeah, we're good, we're good. So we've removed the two last, is that one? No, I don't care about that one. I don't know what this bit is doing down here. I'm not sure what this bit is for, quite frankly, because this is definitely memory. And I'll tell you how I know that, is if we turn the board over, if you have a look at the track layout on the underside of the board, you can see we've got, there's a coil, there's the missing coil, and then there's the +1 coil for the memory. And as you can see, these three here, they're all common together. You can see this big surrounding plane here. However, this guy, he's not joined up to the same plane. So that's how I know that this one is going to the memory, because there's nowhere else it could be going. And this guy is a missing third phase for the GPU. Just notice we're also missing capacitors on the bottom there. There, we need to look very carefully. There could be a lot of supporting components missing on that phase. So we'll get to that though. So yeah, anywho. Right, now we need to get the soldering iron back out, and we need to just tidy up all this stuff. I'm just going to apply some fresh solder to that just to bring the melt point down on it all. And then we can start putting on some nice new MOSFETs. Okay, and let's just mix in some leaded solder. Alright, there we go. So I've now taken all of those down to the pads. So now we're just going to tin them up. So this is the bit where I want to get the amount of solder just right here if I can. So just a touch. So it's quite hard to do this effectively when you've got big ass solder like I have. So I tend to just get a little bit of solder onto the iron and just dab it against the pads until I can see that there is some solder on the pad. Come on, number 2 there is really kicking and screaming. I don't want to overload the pads. We'll get that one in a minute. That's that one. And now we want just a little bit on the base pad. It might not look like there's enough there, but by the time we actually press down the MOSFET package, that solder will smush out in all directions. And we'll touch up the ends on it just for good measure afterwards anyway. So I'm going to roll with that for now. And let's now break out some of our shiny new MOSFETs here. So how many do I need? I need 4, 5 to start with. 1, 2, 3, 4, 5. So as you can see on the bottom of one of these MOSFETs, We've got 4 terminals on one side, and the actual business end of the MOSFET is all common together. So these things are actually fairly generous. And it's all common together like that because it gives a lot of current handling, and it also gives a lot of contact with the circuit board, which means it can heat sink a lot of its heat out through the circuit board itself. So that's for heat management as well. So I'm going to apply some more flux. Make sure there's a little blob on each pad. And we're going to put a FET onto each pad. A little sign in here, a touch of Wi-Fi there. And we'll have your PC ready for all you plan to do. Okay, right, we've lined up all of our MOSFETs. Let's get the hot air on there and flow them into place. Firstly, I need to shut that laptop up. Let's go. Now, all going to plan. These things should... Whoa, yeah, we're not sitting down. Less air. Less air. Sliding about all over the place, and we haven't even started yet. So I need this guy to get up to melting temperature and just settle. Then we back away, press down, and reflow again. This guy's rolling away with me. I think I've started in the wrong direction here. Trying to angle the air so that doesn't skew off course. That one's ready. That one's ready. This guy's going to take a little bit longer because it was further away. He's flowing, but he's not straight. I think that'll do it. Okay, and press and flow. And we know that one's flowed because some big old solder blobs just squeezed out the side. And press. There's the solder blobs. Okay, that guy's not... That guy's a little bit crooked, but I think it's passable. So now we're going to touch it all up with the soldering iron. So now we've got to pick up all of our balls and just make sure that everything is flowed nicely. I'm just waiting for the soldering iron to come up. There we go. Okay, I think we're good. Right, now comes the moment of truth. We need to double check that our short circuit on VCC main, so the main power rail, has not reappeared. Because if that short circuit has reappeared, we are really in trouble because I'll have no idea where that is if it has reappeared. And that'll be a disaster. The last time this card was working was with this phase off the board. We had all those MOSFETs removed. So I'm praying. We did know that the old MOSFET that was here was shorted. That was the original fault. So we should be okay with a new MOSFET in place. Shit. Yeah, we're shorted. Oh no. That's a disaster. Gosh heck. I should have done further testing before we put those back on the board. Okay, right. The first thing we'll do is we'll take off this guy, because that was the original one that was shorted. And if we're lucky, the short will disappear again. And we'll move forward from there. Balls, we're still shorted. Ugh, that's depressing. Okay, let's take off the rest of that phase again. That puts us back where we started. Okay, so to save you another 50 minutes of this already long video, we're going to skip to the point where I've already desoldered all of the MOSFETs and soldered them back on. When I soldered them back on, because they were all the correct way round, the short had magically disappeared. However, because I didn't spot that one of them was upside down in the first place, I didn't notice that until I was editing this video. But at any rate, this is why we do short detection before we power it up for real, just in case. Let's get back to it once I've sorted this out. Alright. Short detection. Cab. Right, so that should be ground. That should not be ground. Cabano. And now it's not shorted. We put the same MOSFETs back on, and now it's not shorted. Fine. I'll take it. Alright. So, we've now successfully rebuilt the original 3+1, 2+1 phases with new MOSFETs on phase 1 and new high sides on 2 and 3. So we've got all matching MOSFETs there, except for those 4 which are old ones, but they're exactly the same make and model. So all of the MOSFETs are the same make and model now. Right, so the next thing we need to do is we need to actually test that the card functions again, because we've got enough of the card rebuilt for it to actually work. So I'm going to take a break now because it's 6:20. I'm going home, and tomorrow I'm going to plug this thing in and we're going to check out if it works. See you after the break. Power switch is there. Okay, here we go. Okay, that looks alright. We have post. Yeah, those MOSFETs are heating up. I can hold my finger to them without burning myself, but it's not doing anything, so that's not surprising. Cool, okay. Let's rearrange it and see if we can capture waveforms now. That's the bit that I want to show you. I want to try and get some science in this as well. Because this whole experiment, the point of me doing all of this is to teach you guys about VRMs, basically. And so I kind of want to demonstrate exactly how they work while we fix them. That's the plan. Okay, so I've got my pocket scope charged up now, and we've got it hooked up with the ground on the heatsink, which is just a common ground. That is grounded through the screws into the circuit board, and thus to just common ground across the whole computer. So what we'll do now is I'll probe the input of the high side MOSFET, and as you can see, we've just got a flat line of 12 volts coming in. So that's coming in from the power supply. So that's just 12 volts. There's nothing fancy about it. And now if we probe the output from the high side MOSFET, we've got a different signal. And if let's just heighten that up. There we go. Now, we're kind of on the limits of what this crappy pocket scope can do, which is why the numbers are all over the shop. However, as you can see, we've got very high frequency switching here. With the peaks are, let me see, VMAX, it's peaking around 4.7, maybe just looking for 5 volts. And then the minimum is down at 0. So essentially, that is where that 12 volts is getting switched on and off at very high frequency by the MOSFET. And because we're working on a scale of 10 microseconds per square on the background there. So obviously we're working at such a high speed that the power doesn't have time to come back up to 12 volts before it gets switched off again, which is why we're not peaking at 12 volts. And then if we probe the input side of the low side MOSFETs, we get the same signal because the input of the low side is connected to the output of the high side. And then the low side is then switching back into ground. So we should see, yeah, there's nothing on the outputs of the low sides. So now if we jump over to the other side, if I probe the input of the inductors, so the big square boys here, so these big squares, on there, we'll see that same signal again. So that's the output from the MOSFETs. And now if I go to the output from the coil, we've got a flat line of 1 volts. Whoops, and then I slipped off. So as you can see, the coil is smoothing out. Oh, for heaven's sake. So as you can see, the coil is smoothing out all of that switching noise into just a flat 1 volt. Or, well, 1.09, you get the idea. Now, it's not just the coil doing that. There's the bypass capacitors and all the rest of it are helping with that. However, it's very difficult to see what the... I don't think we'll be able to see what the bypass capacitors are doing versus what the coil is doing. But you get the idea. So at that point, you can see now how we have 12 volts on the input, then it gets chopped up into a wavy line, and then smoothed out into a lower voltage again. And that is the buck regulator in action. And what these VRMs are, it's just a set of buck regulators. So that all works. Now the next thing that would be really cool to see is if we can see the standby power working. Because we read on the data sheet that the power management chip on this card cuts down to 1 phase at idle. So I really want to see if that is actually in effect or not. And that would be super cool. Now at the moment we're in BIOS, so the card isn't in any kind of power saving mode. So what we'll do is I think I'll get a heatsink on the MOSFETs. We'll get this thing into Windows and put a fan on it because also it's burning up. We'll build the card back up. We'll get the computer into Windows where it has drivers. And then what I'll do is I'll see if I can probe one of the secondary phases to the point where we can see the secondary phase cut in and out at load or idle. That would be really cool to visualize on the scope. I've got Windows installed now, and I was just doing my control test to make sure that we're still in the same kind of situation. But the signal output has now changed. As you can see, we've got just a lot of jitter basically. If I sort of zoom out to this guy, as you can see, we've got a very sporadic switching now. It almost looks like it's either at an extremely low... Well, it's not just a low duty cycle. It's just sort of cutting in and out at high speed. So I'm not quite sure what to make of that. But what I'm going to do is I'm going to restart the computer. And we'll just see how the output from the VRMs change as the display drivers cut in. Houston, we have a problem. Just as I was going to stress test the card, I ran up OCCT and noticed it was only doing 3 frames a second. And I was like, that's a bit odd. However, I haven't spent a huge amount of time with OCCT. It's just a newer tool that I've been testing recently because it does stress testing and temperature monitoring in one app, which is quite handy. So I thought I'll run up Firmark and GPU-Z, which is what I'm more accustomed to, and that has confirmed that we are locked at 135 megahertz on the GPU. And according to GPU-Z, we are at 396 watts power consumption, and that is 330% TDP. So obviously it's locking down. Now it's not actually pulling that kind of power. The card's not physically capable of pulling that much power. However, there's obviously still a bigger problem here. Now, we've seen this card work before and work smoothly. So we know this isn't an issue of the previous time it blew up. So yeah, I'm going to take the card to bits again and have a closer look. I have a suspicion I know what this is. I have suspicion this is going to be the current sense resistor. Which I actually did a video on resoldering lately, and I soldered it using a really dodgy soldering iron. So I have a suspicion that that might be the issue. So I'm just going to check our current sense resistor to make sure that is functional, because it looks to me like that current sense resistor is not reading properly, because the card thinks it's using an awful lot more power than it actually is. So yeah, let's shut it down. It's slightly embarrassing that we've got this problem, because obviously I made that video being like, ha, 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 here's how you do SMD soldering. And in actual fact, that solder joint, by the sound of things, wasn't quite right. But the point of that video was not this is how you repair graphics cards. It was just demonstrating the principles of soldering. So I'll take that as a victory. Oh, come on. Don't make me take off the heatsink. I know it'll come off. Sod it. Alright, heatsink's coming off as well. The heatsink has got to go back on another time anyway, because I haven't put proper thermal paste on it yet. Temperatures are not something I'm particularly worried about at this stage of the repair. So that's the current sense resistor, and the bottom left pad, I don't think that's quite on properly. I don't think I've quite got enough solder in there. So for the video, it was passable. However, I think that's where our actual problem is. There's metal contact there, which is why the card is working in the first place, but I think it's at high resistance. So I think the sense line, which is the bottom left pad, is actually getting a very high read. So it mistakenly thinks the graphics card is using more power than it really is. So let's just get some more solder onto that guy, and then hopefully we'll be absolutely fine. So time for soldering iron. There we go, that's that. I think it just needed that tiny little touch up. I'm not going to look for any other issues quite yet. I'm just going to take that touch up and then see if that's done the job, because that will tell me what the problem was, because I think that was our issue. And if that was it, then that's great. Because if it's not this, it means there might be something wrong with our VRMs, and that makes me very sad, because that's going to be a lot harder to track down. Maybe there's an issue with me changing which MOSFETs we were using. I can't imagine it would be, though. Especially because all the current sensing is being done standalone. You see, on very fancy systems, you have what's called power stages, which is a chip that has the entire VRM self-contained inside it. So you've got, you have that standalone chip that's got MOSFETs, the driver chip, and current sensing and temperature sensing all built into it, and then that just runs straight into the inductor. And that's what you'll see on really high-end stuff, but this is low-end, so everything is discrete, which is why we've got a power management chip, a MOSFET driver, discrete MOSFETs, and current sensing. And the main current sense resistor was this guy, as I pointed out, but there's also little resistors on the bottom there. That guy, that guy, that guy, that guy. Those are all current sensing resistors, where it's reading different current usage at different stages of the VRM. So yeah, that's what that's all about. Okay, right, let's get this cooler back on. And if I'm really lucky, whoa, I just dropped the heatsink onto it, god damn it. And if I'm really lucky, it'll work. So let's get back into it. Okay, GPU-Z, give me good news. Yes! Look, the TDP is normal. And we're not capped. That's all. I'm almost glad we had that issue, because that was another thing that we had to fix. Like, I don't even care if we win or lose in this video now. We've discovered so much in this video. God knows how long it's going to be. I might have to make it a two-parter, who knows. But I hope you guys are entertained, because I'm entertained. I've got work to do, but I can't put this down now. I'm really excited to actually do this, because I've known all of this in theory, and I've seen it all done in other videos, but doing it yourself is a whole new experience when you do the thing, and then it does the thing, and you're like, yeah, it's just like it's supposed to be. So yeah, I'm excited. I'm having a good time. All right, let's do some proper stress testing now. So I need Furmark. Fuck. Oh, it just went bang. Fuck. Oh, it's turbo dead. Oh, it's turbo dead. There was smoke. Oh, no. Oh, no. I spoke too soon. Oh, no. Oh, we're done. We're done. We're so done. That was the inrush. That was the inrush inductors going bang. So we've almost certainly got a short on VCC main again. I guess we'll find out which MOSFET just went dead short. But like, let's have a look. Yeah, we've blown up the input inductors. Let's take it apart. Oh, I shouldn't have said anything. I shouldn't have said anything, but... Oh. Rip in pieces input inductors. Wah, 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 wah. So what we've now experienced is one of the MOSFETs has gone short circuit, which has caused a dead short on the main power rail, and then that has then pulled in maximum current through the input via the shorted MOSFET and blown out the input inductors again. This is exactly what they're there for, to be honest, to stop the whole thing from going nuclear. However, so the next thing we want to know is which MOSFET went bang. That will be super interesting to know. Was it? Well, it would have been one of the high sides, I assume. Let's get the VRM heatsink off. So presumably there is some kind of fault, whatever fault is in this graphics card that caused it to go nuclear the first time round when it first came into my hands. That is obviously still present. So, I'm warming up the hot air station. I'm gonna take off the high side MOSFETs because almost certainly one or both of those has exploded. And those are both the new ones as well. So I'm not sure what that means. Okay, we've got no short circuit. I should have checked it before I took those MOSFETs off. However, we're probably going to find that one of these MOSFETs has gone bang. And if it has, that means that there's still some kind of critical issue with this card that's causing it to blow up phases. But then it didn't... I don't know. It's going to be just with one phase. Yeah, phase 1 has blown up again. Yeah, phase number 1. It's the same as last time. Okay. See, the problem is I don't have more input inductors. Alright, it's time to take a break while I decide what to do with this. See you guys in a bit. Alright, sadness coffee acquired. Let's talk. So, what went wrong? Okay, so we originally rebuilt the VRMs and they did function. and it appeared that everything was okay. However, what was actually going on is due to a soldering issue on the main current sense resistor, the card was working, but it was stuck in a low power state, or rather, it thought it was using more power than it was. Although we were seeing switching activity and all the rest of it, that was good in theory, but one of the reasons why that probably looked janky was because the card was actually heavily power throttling. And then what happened was, as soon as I fixed that and the card was actually able to stretch its legs and open up the taps, it then immediately, phase number 1 immediately went short circuit and blew the arse out of the input inductors again. So how does this affect what I want to do going forward? So this is a trash card. I have no attachment to this. You know, if it's dead, who cares? Boo-hoo. It was dead from day one. I acquired it as a dead card. However, once I had gotten this fixed up, I did actually want to give it to a friend who has like some kind of ancient Radeon 5000 series graphics card. And desperately needs something newer, and this would have been perfect for them. So I'm kind of sad, because the thing is that I can probably put phase 2 back together, bridge out the input inductors again, and the card will work, because that's what we did in the first video where I did the ghetto fix. But the problem there though is that it will be running on a single phase, and if this phase goes dead short with the input inductors bridged out, then this thing is going to go bang big time. And I mean, I guess it'll be contained, but I don't know. I don't want to give the card away if I know full well that it's likely to fail. I mean, hell, we could just fix it back up single phase and actually give it the beans and see what it can do, because we never really gave it full testing the last time with the ghetto fix, because I didn't have a working fan for it, whereas now I do have a proper cooler for it. So maybe we can see if it really can run single phase. The other option is I go back to the original plan, rebuild the missing phase, and see if we can get 2 working phases out of that. However, also, you know, while I was making the coffee, I was having a closer look at this, and the thing is, there's more to building up this phase than just putting on some MOSFETs and another coil. We've got to put on the driver chip, and we can steal one from the donor card, or we can just move the phase 1 driver chip across. But also, there's lots of tiny little resistors, presumably to program the driver chip. And on the other side, we've got to build up the bypass capacitors, the current sense resistor, and the small resistors going to the current sense resistor. And just, man, that is actually quite a big job. And throughout this entire video, although I've been talking about wanting to have a go at that, I have been sort of going, we'll see if we get that far kind of thing. Truth be told, if it had been fully functional with those 2 phases running, I probably would have quit at that point and said, we could build up this phase, but I'm going to quit while I'm ahead. Alternatively now, yeah, I mean, we could just say, we could just say, fuck it, let's try it. And just go death or glory on this thing. Let's run it single phase again. I'll bridge out the input inductors. We'll run it single phase again, and we'll see if it blows up that phase. And let's go from there, and we'll see what we get. Oh, such a shame. Can't believe, literally seconds after I was just saying how much of a good time I was having. Gosh, heck it. It's like the hospital receptionist who commented that it was a quiet night. It's terrible, Muriel. Right, cooler's going back on. Just thinking, I didn't really look into the problem very much last time, but we have to consider the fact it was the shorted MOSFET that I threw out. That was the high side MOSFET that had gone dead short circuit. But the thing is, that MOSFET doesn't have a path to ground. So how did it go short? Let me show you the schematic again. So that's our high side MOSFET there, Q1. And as you can see, it's got the 12 volt coming in. It's got the drive high signal coming from the driver chip. And then its output goes through to the coil. And then there's the low side MOSFET. So the high side MOSFET doesn't have a way to get to ground. And if this capacitor C4, that'll not be that capacitor will be fine, because if C4 had failed, then the card would not be the MOSFET wouldn't have blown up. We would have gone short circuit through C4, and C4 probably would have exploded. C1 has gone dead short, so in order for that to achieve a dead short circuit, it has to go through the low side MOSFETs. But the low side MOSFETs are fine. Who knows? I'm not sure. I'm a bit confused as to what might be going on there, but it's hard to tell. At the very least, though, so yeah, that's all a bit confusing to me. But on the other hand, at this point, I don't really have any desire to try and fix phase 1, because I'm 99% certain it'll blow up again. So yeah, I think at this point now, I'm going to simply try and get a working graphics card out of this and then quit. So let's get this thing plugged in and we'll see if it can work. GPU Z, let's go. Show me what you got. And I want Firmark. Right, so we're up to 88% TDP, power limited, and we're running at 1253 megahertz. So the card is operating normally. Once again, that VRM, just like it did the last time we were running it on a single phase, does not sound happy. There's a lot of coil whine. Well, there's not a lot, but I can hear that VRM working. In any case, I'm going to leave this to run and we'll see if it can actually tank load for a while. Alright, this has been running for half an hour now and I'm bored, so we're moving on. The temperature has stabilised. It's been sitting at a flat 70 degrees, which is obviously what it's targeting for quite a while now. GPU clock has settled at 12:15, so it's gone down a little bit. We could probably maintain a slightly higher boost because, again, I haven't thermal pasted this properly or anything like that. So there's more cooling to find in this. And the fan is running at 46%. It's actually quieter than I expected it to be. It's not bad. So yeah, this cooler is actually doing a reasonable job on this card. In any case, it seems to work just fine. I think if that, like, running it single phase, we've probably shortened the life of the MOSFETs significantly. But just like when you're overclocking, let's say you cut the life of the MOSFETs in half. So you take a graphics card that would last 10 years and you make it only last 5 years. Who cares? We're not expecting to use this graphics card for 5 years anyway. This thing would only need to last for maybe a couple of years at most. So you get the point. Even if I've drastically shortened the life of the card, it still doesn't really matter. So we've got something that works. Right, so I've done my investigations, and what I did was, the first thing I looked at was the MOSFET driver chips. I looked up the data sheet for those. Those were they're on semiconductor, and they were NCP 81062 chips. They don't have NCP written on them, and they don't have ON written on them either. However, because the MOSFETs and the power control chip are on semiconductor, these regulators are going to be as well. They'll use the same family of chips because they're designed to all work together. So looked up the spec sheet for those, and they're pretty simple really, and the implementation is very straightforward. We've got 3 of them implemented on this board at the moment. So we have a chip, then there are 2 resistors coming off of it. Now the missing pad, we've got the missing chip, and the 2 resistors are missing, and we've got an extra one there. That extra resistor is on the PWM input line, so presumably that is either a pull-up or a pull-down resistor to prevent ringing, because if the PWM signal comes down that signal wire, what they don't want to do is they don't want it to echo off of the end of the trace and bounce back or do anything weird like that. So they'll have this resistor place on it just to dampen the signal. So the signal goes out, but just nothing happens to it. It just goes down and there's no echo or anything like that. So what we would do is we put a chip on there. I'd take it off the donor board that I've got. We'd remove that resistor and place 2 resistors there and there that I would take from the donor board. So far, so good. Then we can populate our 3 MOSFETs, and we need to put there's a capacitor that should go across there that matches up with these ones. So far, so good. But then the problem is when we get round to the back of the board, this is where I ran into trouble. Once again, on the back of each phase, you can see we've got 3 bypass capacitors on the back of the high side MOSFET. Not a big deal. We can put those on there. So there's the pads for them. We put one there, and one there. That's no big deal. And then additionally, there are 2 capacitors that go on the back for the driver chip that probably go there and there. I'd have to buzz out some of the pins to confirm that, but because I have the data sheet for the driver chip, we know the pins, we can buzz those out and verify which ones they are. I was going to do a sequence where I show how to do that, but I won't bother showing you that because of reasons, which we'll get to in a moment. But the point is, we put a capacitor probably there and there. And there's basically nothing else that needs to go back here. There are some resistors down here, but none of them are in use, I believe. But the reason why I stopped moving forward now is, again, we put an inductor across there as well, no problem. There's some bypass capacitors up here. So again, we've got, there's one there. So we're probably going to go one there and leave this guy unpopulated because he is over there as well. And he's also unpopulated over here. So you can see how we can build it all up. But on this one, we have what are presumably current sense resistors all across here, and they have some supporting resistors and capacitors around them. But on my donor board, they're missing. They're not populated on my donor board. So this also had different MOSFETs on it as well. So this, despite being an identical reference board, let's see, E307069. There we go. E248779. So again, these are both, like, look, they're literally identical, but they're obviously just from a different run because they've used different components on them or something like that. But now this introduces the problem, is that on this one, because they haven't implemented those current sense chips, I don't know how critical it is to have those on the board. And because I don't have the current sense resistors, I don't have the donor parts that I need. So although we've got like the capacitors and things like that, I don't have the spare current sense resistors. And I don't want to disassemble phase 1 any further. I just want, at the moment, I can disable phase 1 just by removing one of the inductors, no problem. But I don't want to leave phase 1 half dismantled. I just want to leave it with no input, because otherwise funky stuff might happen. Again, we might get stuck in a low power state or something like that. So the long and the short of it is, while you can see that it's absolutely possible to populate this extra phase if we had the parts, unfortunately the donor card that I was going to get the parts from is missing some of the parts. So on that note, as far as I'm concerned, I've hit the end of the line. But I have hit the end of the line with what is technically a functional card, albeit a functional card with only one working phase. So honestly, I think I'm going to quit while I'm ahead. I'm going to clean this up a bit. I'm going to put some fresh thermal paste on it, and I'm going to give this card to my friend and say, here's a free 962 gigabytes. There's no warranty on this. They just want to poodle around in the Sims and things like that. So I have a suspicion that they'll be absolutely fine with it. It took 30 minutes tanking full load, you know, as long as they don't start mining bitcoins on it for a week on end, I think they'll be all right, to be honest. And if it goes pop, then so be it. If it goes bang, then it's probably going to cut out the computer, because with no input inductors, it'll basically just trigger the overcurrent protection on the power supply and the computer will cut out. So that's the end of that. Past that, I think I'm going to throw in the towel on this one. So yeah, not the ending that I'd hoped for, but at least we're coming out with a working card that will have a functional cooler on it, so it'll actually be usable, unlike the last time I fixed this card where it was not really usable in the real world. So I hope you guys learned a lot about VRMs and buck regulators on this. I certainly had a lot of fun experimenting with this, so I hope this video comes out well in editing. It's been a bit of a roller coaster. So yeah, thanks for watching everyone. I'll see you all next time. Bye for now.